In this fourth video on simple regression, we'll examine how one statistically tests a regression coefficient. In the previous video, we discussed using regression to partition the variance in our outcome variable so that it was divided between the variability related to our regression model and that residual variability that we didn't understand, at least yet. We then discussed the F-test, just like in ANOVA, that tested whether the model accounted for enough of the variance using our sample data that we were confident whatever effect we saw in our sample was in fact real in the larger population. The F-test in regression examines the variance in our model, how much variance in the outcome we can account for. But we can also ask similar questions about our regression coefficients, particularly the slope. Remember, the slope of the regression line is b1, the regression coefficient for our predictor x. For example, in this hypothetical case, our predictor is the amount of time parents spend reading to their child, and the outcome we're predicting is the child's reading ability. Let's get rid of the data points in our figure and only focus on the regression line for a minute. If we think about this conceptually, we can see that if the slope for our regression line is equal to 0, if we make the regression line flat, x has no effect on the outcome. When predicting y, our y hat, we're multiplying x by 0, so it doesn't matter whether you're high or low on x, you're always going to pick the same value for y, which in fact would be the mean of y, but I digress. When we test the regression coefficient, we're trying to determine whether we're sufficiently convinced that the slope, b1 in our sample, is so different from 0 that it's unlikely that this is due just to random chance. In other words, is the slope sufficiently large that we would have only randomly stumbled on a sample with a slope this large or larger less than 5% of the time if the slope in the overall population really is 0? If so, we can conclude that we're probably not that lucky, and in fact the slope, or the effect of x, in the population is not 0. There is an effect. Now, to actually test a regression coefficient, we have to go through several steps in calculations. Fortunately, the technology does the heavy lifting here, but it's good to see how this works because some of the same principles involved will keep coming back. So first you calculate the variance about the regression line. You then use that to calculate what we call the standard error of the estimate. We then use the standard error of the estimate to calculate the standard error of the regression coefficient, or the standard error of B. We then use the standard error of B to perform a t-test in order to determine whether our regression coefficient in our sample is sufficiently different from 0 that we can reject the null hypothesis that the effect is 0 in the population. The t-test tells us whether we're sufficiently convinced that any effect we see in our sample is in fact real. The variance of the estimate is the variability that we see in the scores about the regression line. It's the variance of the residuals. Mathematically, you may see it written as s squared, a variance, sub y dot x. The y dot x tells us it's the variance in the y residuals when we have x in our regression equation. This is also called the mean squared residual, often referred to just as the MSR. Now, why call it the mean squared residual? Well, because it's kind of the mean squared residual. It's equal to the sum of our observed minus predicted score squared, y minus y hat squared, divided by n minus k minus 1. But wait a minute, we've seen this before. The sum of our observed scores minus the predicted scores squared is the sums of squares residual. And n minus k minus 1 is the residual degrees of freedom. So you may also see it written as the sums of squares residual divided by the degrees of freedom residual, which sure sounds like the variance of the residuals around the regression line, which is good because that's what it is. The next step is to calculate the standard error of the estimate. This is just the standard deviation of the residuals. And given we know that the standard deviation is the square root of the variance, it's just the square root of the variance of the estimate. Mathematically, it's written as s sub y dot x. No s squared now because we're taking the square root. The standard error of the estimate is the square root of the mean square residual, or the square root of the sums of squares residual divided by the degrees of freedom residual. We then use the standard error of the estimate to calculate the standard error of b, the standard error of the regression coefficient. Mathematically, the standard error of b is written as s sub b. That's because it's effectively the standard deviation s of the regression coefficient b. You may also see it written as se sub b. Don't worry, it's the exact same thing. Different sources, sometimes even the same source, may use both notations at times, particularly if there's a lot of S's floating around and they want to make the distinction between those standard deviations and those standard errors. So S sub b, the standard error of b, is equal to the standard error of the estimate. Remember, that's our standard deviation of the residuals, divided by the square root of the sum of x minus x bar quantity squared. But hey, the sum of x minus x bar quantity squared in the denominator is the sum of squares for x. So far, when we've been talking about the sums of squares in statistical tests, we're talking about the sums of squares for the outcome variable, y. This here in the denominator is the sum of squares for our predictor. That's pretty different, and it has some interesting consequences that are very important when it comes to designing a research study. We'll talk more about that later, but for now, I just want to emphasize that this denominator is the sum of squares for x. But again, usually, unless you're told explicitly otherwise, when we talk about sums of squares and partitioning the sums of squares, we're talking about the sum of squares for our outcome variable. Now, returning to the standard error of b formula, as a result of all this, you may also see the standard error of b written as the standard error of the estimate divided by the square root of the sums of squares of x. Now, the key is to think of the standard error of the regression coefficient as the standard deviation of slopes or effects that we would see if we replicated this study an infinite number of times. Thinking all the way back to our videos on variability and z-scores, it gives us our yardstick to measure just how big our regression coefficient is. Using the standard error of b as our yardstick, there's two ways we can approach assessing our regression coefficient. The first is through traditional null hypothesis testing, conducting a t-test and calculating the p-value. We'll deal with that now. The second way is to estimate confidence intervals. We'll save that one for the next video. To see how we use the standard error of b in null hypothesis testing, let's clear off all of the data points again and focus on the regression line. And let's add the horizontal line that we would see if the slope in the population was really equal to 0. In fact, we can think of this as our null hypothesis regression line or slope. Even if the null were true and the slope in the population really is 0, any random sample will probably not have a slope that's exactly 0. It may be a little greater than 0 or a little smaller than 0. If we collect an infinite number of samples and graphed all of their slopes, we would see a distribution of slopes, centered on 0, but a little positive half of the time and a little negative half of the time. Based on the standard error of the regression coefficient, this shaded area illustrates the distribution of slopes that we would see if the null is true. How large it is, how spread out that distribution is based on the standard error of B. The question then becomes whether our observed score is sufficiently extreme to reject the null hypothesis. Is it so large that it's highly unlikely we would have randomly ended up with a sample where the regression coefficient is that big if the real value for the effect in the population is 0? If it is, then I can reject the null and conclude that it's just too unlikely to be random. The effect or slope in the population is not 0, and I can reject the null hypothesis. Now, if we pause for a moment and think about it, this is starting to sound a lot like a one-sample t-test. In the one-sample t-test, I have a value for the mean that I expect to see if the null is true, and I have a standard error of the mean as a measure of the variability in the sampling distribution of means that I'd see if I sampled an infinite number of times over and over again. And I have my observed mean that I want to compare to the null mean. And I want to know whether that observed mean is sufficiently extreme that I can reject the null hypothesis. To do that, I use the standard error of the means as a yardstick to look at the difference between my observed mean and the mean if the null hypothesis is true. I'm basically doing the exact same thing in regression. In regression, I have a value for the regression coefficient that I expect to see if the null is true. That's 0. I have the standard error of the regression coefficient as a measure of the variability in the sampling distribution of regression coefficients, or slopes, that I would expect to see if I sampled an infinite number of times. I have my observed regression coefficient, the slope we found in our study, that I want to compare to the expected value for the coefficient if the null is true. That's 0 again. And I want to know whether my observed regression coefficient is sufficiently extreme that I can reject the null. To do that, I want to use the standard error of the regression coefficient as a yardstick to look at the difference between my observed coefficient and the expected value of 0 if the null is true. Beautiful! It's identical to a one-sample t-test. I've just replaced means with regression coefficients or B's. So let's do a one-sample t-test. The t-test for our slope is just t equals b1 minus 0 divided by the standard error of the regression coefficient. As you can see, it really is just a one-sample t-test. Now, because we're comparing the observed slope, our b1, to 0, you'll generally see it written just as b1 divided by the standard error of the regression coefficient. The degrees of freedom is just n minus k minus 1, where k is equal to the number of predictor variables in our model. In simple regression, where we only have one variable, k is equal to 1. Now, of course, this is written for testing the regression coefficient that corresponds to the slope in simple regression. But it's the same t formula and the same degrees of freedom formula in multiple regression, where we'll have different b's and different standard errors for each of the different variables in our model. Now, it's worth noting that while we almost always compare our observed regression coefficient to 0, you don't have to compare it to 0. There may be some other known or expected value for the slope to which you want to compare your observed effect. You can use that value instead. You just plug it into the t-test equation, calculate your t-score, and make sure you interpret it correctly. Okay? So This wraps up our conversation on testing the regression coefficient. In our next video, we'll look at the other way of assessing our regression coefficient, and that's using confidence intervals. Should be good. Okay, see you then. Bye-bye.